And this is from some very beautiful work done by the UCLA research group of Professor Andrea Ghez at UCLA. Her group has used the Keck telescope for many, many years to monitor the positions of stars that are orbiting around the very, very center of our Milky Way galaxy. So every little data point here is the position of a star measured at one particular occasion. And these stars are all orbiting around one common point right there. And what do we see at that point? Absolutely nothing. But from the orbits of those stars, they can measure the mass of the invisible thing that's at that exact point. And it turns out to be 4 million times greater than the mass of the sun. So this is one of the best pieces of evidence for supermassive black holes because it's so close and it's possible to track the orbits of individual stars. And in fact, this star that did almost a complete U-turn around the black hole, that went very close to the black hole. The distance from the black hole to where that star made its closest approach is about the same as the distance between the sun and Pluto. So that star had a very, very near miss with the black hole. But now other galaxies that we'd like to study are so far away that we can't possibly do measurements like this when we look at other galaxies. When we look at the center of another galaxy like this, which might be a little bit like what our Milky Way might look like if we could step outside of it, what we see is that there's this disk of stars, sort of a flattened disk. There's this central spheroidal region, which is sometimes called the bulge of the galaxy because it's a spheroidal region that bulges out of the central disk. And we think that in the center of every galaxy bulge like that, there ought to be a big black hole, but all we can see is the combined light of millions of stars at the center of that galaxy. We can't track the orbits of individual stars in other galaxies like this. But there are methods that astronomers have developed and used quite a lot over the last decade to use the aggregate motions of stars in the centers of galaxies like that to infer the presence of black holes. This has been done a lot over the last decade using data from the Hubble Space Telescope. And now we can start to do work like this at the Keck Observatory as well and some other ground-based telescopes using a special technology called adaptive optics that measures and compensates for, in real time, the blurring effect of the Earth's atmosphere. And it can give us data that is, in fact, comparable or sometimes even better in terms of its sharpness than what we can get from the Hubble Space Telescope. So I'm going to just show you a few bits of work in progress by my research group to illustrate how these measurements are done. Measurements like this have been done for a few dozen galaxies before with the Hubble Space Telescope by a variety of groups around the world. The basic idea is we want to really zoom in as much as we can on the central region of that galaxy to see what the stars are doing. And using the adaptive optics system at the Keck Observatory and a special new spectrograph called the OSIRIS spectrograph, we can obtain data in a very, very small patch of light from the very, very center of that galaxy. And using this OSIRIS spectrograph, oh, sorry, this is a little bit cut off here, missing the bottom of my picture, but we can zoom in on the inner few hundred light years of that galaxy. And with this special spectrograph, at every point in this grid, we can obtain a spectrum of the starlight that we see. And that starlight is the combined light of millions of stars that are all orbiting around the black hole in different ways. But what we expect to see if there's a black hole is that as we look closer and closer and closer to the center, the stars should be orbiting faster and faster and faster because of the gravitational pull of the black hole. And here's an example of just to show you, this is work in progress and we don't have the final answer yet for this galaxy, but just to show you what the data looks like. These are spectra taken at infrared wavelengths, longer wavelengths than what we can actually see with our own eyes. And if we look at a little piece of the spectrum of light, we see these absorption lines, these spectral lines that come from particular molecules in the outer atmospheres of red giant stars. These particular strong, sharp features come from carbon monoxide, actually, in the outer atmospheres of stars. And when we look at the light of the galaxy, we're seeing the light of millions of stars combined together. And some of those stars are going to be moving away from us, and their light will be red-shifted. Some of those stars will be moving towards us, and their light will be blue-shifted. So all of those stars are going to have different red shifts and blue shifts. And the combined effect of all their light added together is that we see the same spectral lines in the light of the galaxy, but those lines are blurred out and broadened out by the fact that some of those stars are red-shifted and some are blue-shifted by different amounts. So we can measure the amount of that line broadening compared to the line widths that we see in a single star, and we can use that to infer the aggregate stellar velocities in every little region in this galaxy. And the result of that, we hope, will be that we'll detect an increase in the aggregate stellar velocities toward the center of the galaxy, and we can use that to infer the presence of the black hole. Work like that has been done for a few dozen galaxies in the past, again, mostly with the Hubble Space Telescope. And now with this exciting new capability to do these measurements with adaptive optics, we're starting to do this kind of work at the Keck Observatory as well.